Welcome to another lecture of Psychology 101. This is Dr. Shadi Bashai, and today we will continue talking about psychological approaches to research methodology, and this again corresponds to Chapter 2 of your textbook. So, in the last lecture, we ended by talking about reliability and about validity. And I promised you I'll talk about it a little bit more this time, and here we are. So reliability, if you remember with me, is the ability of a scale or a measure to measure something consistently across time and across situations. And there are several types of reliabilities. The first of which is what we call test-retest reliability, which is if you give the measurement over time, so you give the measurement to the same person over time, are the results consistent every time you give it to that person, especially if it's a psychological variable that we're trying to assess, for example, that is relatively stable, and for that reason you expect it to be you expect that person to obtain a similar score every time they're tested across time. Okay, so let's say I develop a new measurement of IQ, and I give you that scale or that measure once in January, and then another time in December of the same year. Now, there is no theory that I know of that tells me that IQ can shift over a year. So if the scale is said to have test-retest reliability, then it will show a very similar score in these two time administrations. Okay, and then there's inter-rater reliability, which is consistency of the score, even if it's scored by two independent reviewers, if you will. Okay, so I'll give you an example of what that looks like. Let's say you're a client and you come to me and you describe what essentially is symptoms of depression. And I score you and I give you and I say, you have depression. And now let's say you take that diagnosis and you say, you know what, I want a second opinion. And you go to my colleague next door who uses the exact same measure I did and also comes up with a diagnosis of depression. And if that happens, then the measure that we used, both myself and my colleague, is set to have inter-rater reliability because two independent reviewers or scorers came up with the same consistent score for that one individual. And then there's internal reliability, which is how well do items of a measurement or of a scale hang together, meaning many of the psychological symptom scales that we use have multiple items. So items, 1 to 10 or 1 to 20, or some even have 500 items. Okay, so if all these 500 items or these 10 items or however many items, if all of them are approximating the same concept, let's say depression or anxiety or schizophrenia or psychosis, whatever it is, if all of these items are approximating the same thing, they will come to the same conclusions, meaning they'll be very highly consistent or correlated, and they'll hang together because they're all, again, measuring the same concept or the same construct behind the scenes. And we also talked about validity, which is whether the measurement or the scale or the tool that I'm using is actually assessing what it purports or says it's going to assess or measure. Okay, and there are, much like reliability, there are multiple types of validities. I'll give you an example of two here. Okay, which is criterion validity, and criterion validity is broken up. Overall, it's defined as I'm going to test whether something is accurately measuring something by putting it against some kind of a benchmark, and I'll make it real. I'll give you a concrete example of what that looks like. Let's say that I have a new measurement of IQ, the same measurement that I've been talking about now, and I want to assess whether it's valid. So what do? So we know from theories related to IQ that IQ should be predictive of things like scholarly achievement, or things like how well you do on the job. Okay? So if my scale is to be valid, then it has to predict how well you'll do on the job and how well you'll do in schooling. And we call that criterion validity. It sums up the accuracy of the measurement against some kind of a benchmark out there in the universe, out there in the world. Okay? And there are two different types of criterion validities. There is concurrent validity, meaning the benchmark is happening right now. It can be measured currently, or it could be predictive validity, meaning the scores that you have on the measure that you're trying to test is predicting something that's going to happen in the future. For example, how well you'll do once you graduate university, let's say. So that's criterion validity, with concurrent and then predictive. And then you have face validity. And face validity asks the question, does it look like it's actually measuring the thing that it says it measures? Okay. So for example, if it's a depression scale, maybe the first item is, are you depressed? Maybe another item is, are you sad? And if the scale of depression is set to have these items, then it is also set to have face validity because it looks like it's measuring what it said it's going to measure. So in big scale types of self-report measures and surveys, sometimes what you'll see researchers doing is that they'll create norms, meaning they will give the scale that they're trying to validate to a big representative population, and the reason for that is they're trying to establish a norm as to how well people do on that measurement, for example. Okay, and a really, really important example of this, one that comes to mind immediately, is this idea of IQ, right? So they give brand new IQ measures to a large segment of the population that is said to be representative, and then they actually start analyzing the scores, and for the most part, IQ measures have a distribution that looks like this one. Okay, this is the bell curve, or what psychologists like to call the normal distribution. And the reason why it's called the normal distribution is because it falls within very predictable segments, and therefore you can actually, if something is measured in this way, you can, based on someone's scores, you can figure out how much of the population they're outperforming, or how much of the population is actually outperforming them. And this is the concept of percentile rank, which is basically based on a big normative sample of how well people do on a particular scale or a particular measurement, such as IQ, right? You say that you're in the 50th percentile, and if you're in the 50th percentile, it means that you score above 50% of the population on IQ, and there's 50% of the population that scores above you. And if you're in the 90th percentile, for example, it means that you score higher than 90% of people who do take that test, and only 10% are ahead of you. Okay, so that's what norms and percentile ranks mean. And then there's the concept of standardization. So let's say my measurement is trying to get at IQ, right? So that's the new measure that I've just developed. I want to do the best that I possibly can to eliminate other things that may interfere with getting an accurate picture of someone's IQ. Okay, and for that reason, we try to nullify the testing conditions, the administration of the IQ measurement. We try to make them all very consistent across testing centers, across researchers. For example, if you're giving an IQ measurement, oftentimes what will happen is you'll be highly trained, and you'll need to be a psychologist, for example, in training. And the reason for that is there's a very specific way that you have to administer an IQ measure, and the reason for that is it's for standardization. Okay, so that if we get different scores depending on who we're measuring, so we get two different IQ measurements, one from Sally and one from Susie, and we know that Sally has a higher IQ. If we know the administration was standardized across both Sally and Susie, we know that the difference in their score is actually reflective of the differences in their intellect or their IQ. Okay, so that's why we do standardization. It's a level of control. And we talked about the normal distribution here, which I'm sure I'll be talking about in many other lectures as well. So just to sum up here, because we've been talking about self-report measures a lot, because we do use them quite frequently in psychology, actually. So the pros of self-report measures is that they're very easy to administer. Oftentimes, they're just a handful of items, right? Like 8 to 10 items. They're a very direct way to get at whatever it is that you're interested in getting at. So take, for example, if you're interested in knowing how often people have felt depressed over the last couple of weeks, it's a very direct way to do it, just to ask people, how often have you felt depressed over the last week? So the pros, easy to administer, very efficient, and very direct in the way it measures things. And there are several cons, however. Okay, and again, it's always a trade-off with these things. One of the cons is sometimes there are certain characteristics of people that make them more likely to be dishonest. So more likely to, for example, exaggerate their abilities. Hard to do on things like IQ tests, mind you, because they're very behaviorally based. But on things like, if I'm asking someone about how impulsive they are, for example, they can really downplay their impulsiveness if they want to paint a picture, a certain picture of themselves to me, right? So people could be potentially dishonest. People can have an idiosyncratic way that they approach the measure itself. We call those response sets. And this is the tendency to systematically answer a scale in a certain way. And I'll give you an example of what that means. So what that means is, let's say my personal learning history, who I am, makes me more likely on a scale of 1 to 5 to answer always 3. Okay, so that can obviously systematically skew the responses that I have on a self-report measurement. So there's that, and then there's positive impression management. Maybe I want to paint a picture of myself that I'm better than how I'm actually doing. You know, maybe I'm trying to suppress a few psychological symptoms that I don't want people to know about. Okay, so I can positively impression manage. Or the opposite of that, I can malinger to get some kind of a secondary gain. And malingering or faking, let's say faking of psychological symptoms, faking of memory issues or whatever, these things happen especially in small claim disputes. They happen in compensation disputes, etc. So this is when people have some kind of a secondary gain they're getting out of it. They fake bad, as we like to call it. So there are cons, of course, to using self-report measures and using them almost exclusively. But there are measures that are put in place that we can minimize the bias arising from these self-report measures, or to minimize the cons of using self-report measures. So, for example, we can corroborate the reports of the self-report measure. So let's say I give you a measurement of how depressed and sad you've been over the last week. So I can take your self-reports, and then I can go and ask your partner or your parents or your friends the exact same questions that I asked you, and kind of juxtaposition both of these answers together and kind of come up with a conclusion, right, based on your own reports and based on other people's reports. So that avoids some of the problems that we see in self-reports. Part of the problem, of course, is that it's extremely expensive, and hardly anyone ever does that. It's just not time efficient at all, and it's very difficult to bring in people that the person knows. It's a mess. It's a mess, really. And there's another problem, of course, beyond the fact that it's a very difficult, inefficient thing to do. There's the halo effect, which is the tendency for one positive characteristic about an individual to spill over into positivity or perceptions of positivity about other traits. So if you find the person attractive, you're also more likely to think they're honest. You're also more likely to think they're trustworthy. You're also more likely to think they're more successful. And we call that the halo effect. And that can, of course, also skew corroborating reports, okay, which is something that is very, very difficult to avoid, unfortunately. So now back to our discussion of the different tools in our toolboxes. One approach, one design that is often utilized in psychology is the correlational design. And what correlational design means is that we're assessing how much change in one construct or one variable is happening simultaneously with change on another variable of interest. Okay, so basically, how closely does change in one follow with change in the other? And I'm being very careful to say with, not because of, because remember, one of the core principles of science is correlation is not causation. Just because two things are moving together, they're changing together in time, doesn't mean that one is causing the other. Okay? Correlations can range from anywhere from -1 to +1. So if it comes close to 1, it means the relationship of change is almost perfect. Meaning that if it's a very consistent co-change between variable A and variable B. Change of 1 unit on one is equal to change of 3 units on the other, and that's always consistent. That will be a correlation closer to 1 if that happens. The closer you actually move into 0, so a correlation of 0, so the smaller that number gets, regardless of whether it's positive or negative, and we'll talk about what that is in a second, the less the correlation or the degree of correspondence between the two variables. Okay, so the closer to 0, the smaller the correlation. The closer to 1 on either side, plus or minus, the stronger the correlation. So a correlation could be positive, meaning that change in one variable, increase in one variable is associated with also increase in another variable. So they move together in the same direction. And it could work the other way too. So a positive correlation could also mean going down in one also means going down in the other. And I'll give you examples of what that is. So there's a positive correlation between depressive symptoms and social withdrawal. So the higher the depressive symptoms, the higher people tend to withdraw into their homes or withdraw from social environments, etc. And then the correlation could also be negative, meaning as one increases, the other decreases. And I'll give you an example of what that might look like. As you increase your intake of alcohol, your coordination decreases. Okay, so there is a negative correlation here between alcohol intake and coordination. As one goes up, the other goes down. Okay, and then finally, it could be a 0 correlation. Like I said, the closer it is to 0, it means there's hardly any relationship or correspondence in the change of one variable with the other variable. And this is what they might look like graphically. So if it's a positive correlation, it'll be tilting upward like that from the left to the right. If it's a negative correlation, it'll be tilting downward from left to right. And if there's no correlation, then it just looks like a scatter of dots, like you see on the graph in the far right here. And again, I want to remind you, correlation is not causation. Just because change in one corresponds to change in the other doesn't mean that one is causing the other. And I'll refer back to the Hawthorne effect, right? Just because they changed the light and they saw an increase in output, in performance, just because that happened, doesn't mean that the lighting conditions caused the change in output and performance. What ended up actually happening is that it's not because they changed the lighting conditions, it's because people's performance was heavily scrutinized during that period of the Hawthorne studies. Okay? And that's really, if you observe people's behavior, they'll try a little harder, it turns out. And there's another set of studies, which is the hormone replacement therapy studies. Back in the 1960s and the 1970s, there was a study that found that there was a correlation between taking hormone replacement shots when women were in the midst of menopause. Okay, so many women were prescribed hormone replacement therapy to lessen the effects or the symptoms of menopause. But the study found that there was a correlation between taking hormone replacement therapy and reduced incidence of heart disease. It was actually almost protecting people from heart disease. At least that's what the media started saying at the time, was that, hormone replacement therapy can prevent heart disease. It turns out that it wasn't really the hormone replacement therapy that was causing the change in the profile in chances of getting heart disease. It was the fact that women who were taking hormone replacement therapy happened to be, more often than not, more affluent. So they had better diets. They were more likely to exercise. They were more likely to avoid junk food, less likely to smoke. So that's, again, when we confuse a correlation with a causation, lots of confusion can happen, unfortunately. And then there's a final video here, which shows when a correlation was confused with causation around the time of polio, when ice cream was believed to be associated with polio. And if you're still not convinced that correlation is not the same as causation, here's yet another example of how that could be pretty bunk. This is the first graph is on your left, and it is the correlation of Nobel laureates per population density and consumption of chocolate. And if you draw a line across these different flags, there is a very strong correlation of 0.79. And this is on the right here is a graph of the correlation of global average temperatures with number of pirates, not pilots. It's ridiculous either way, to be honest. But of course, again, it's another example of how correlation is not the same as causation. Here is another depiction of how correlation can be positive, can exist not at all, and it could be negative. So on the far left here is a graph of a negative correlation. This is the exam grades with the number of beers. And there's no correlation, turns out, between exam grades and shoe size. That's the middle graph. And the far right graph is psychology exam grades with the percentage of classes attended, okay, which is a positive correlation. Again, I cannot stress this part enough. Correlation is not causation. It is not the same thing, okay? And the reason why I'm stressing it so much is that it is often and ubiquitously confused in pop culture. It's ubiquitously confused, and sometimes even deliberately, actually, in the media. Okay, so I'm really trying to make you a very skeptical and critical consumer of what's out there. And there's a lot of crap, unfortunately, out there. So we talked about correlational designs. There are also epidemiological studies or epidemiological designs. And epidemiological designs are survey-based, and what they do is they administer surveys to a large, massive sample size and as representative to the population as possible. And epidemiological studies are really interested, for example, in figuring out prevalences, which is how often the base rate of how often a problem happens in the general population. For example, the prevalence of schizophrenia is 1% in the general population. Okay, so we call that the prevalence, overall rate of cases. It's also interested in understanding things like incidence, which is different than prevalence. Incidence is interested in examining change in the prevalence across time. And if you find a new case that is not accounted for by the previous timeline, then you say that there's an incidence of 1. There's a new case now. Last year it was 20, this year it was 21. So the incidence, let's say, of that particular problem is 1. So epidemiological research is very much used for this type of question, which is how often does a problem occur in the general population? How fast are we changing as a population? So on and so forth. And then there's the holy grail of all research methodology, okay, of all designs, which is the experimentation. And in true experiments, as is always the case, there is what we call an independent variable and a dependent variable. And let me tell you what those are. An independent variable is the variable that we manipulate in our study, and then the dependent variable is the thing that we're expecting to change based on the manipulation we did in the independent variable. Okay, so if that is confusing, let me give you a real example. Let's say I'm trying to figure out whether room temperature has anything to do with aggressive behaviors. And let's say I run an experiment and I operationally define what that means is I give a very concrete definition of what aggression is. And I say aggression is anytime somebody does A, anytime somebody does B, anytime someone does C. And let's say I get a big representative sample from the population, and I assign them to 2 conditions. Okay. In one condition, they are to wait. So half of that sample, that large sample that I got from the general population, half of them are to wait in a room that is set to a very comfortable 22-degree temperature. The other half are assigned to a room or a condition where the temperature is set at a much higher temperature, 30 degrees. And then I have observers in each room count the number of instances when somebody does an aggressive act based on how I defined what an aggressive act is. Okay? I hope you're following with me here. And then I count basically the number of instances of aggression in either condition, and then I figure out whether room temperature has anything to do with aggression. So in this particular example, the independent variable, the thing that I manipulated, the thing that I changed, that I tweaked, was the room temperature. And it had 2 conditions. It had first condition of 22 degrees, I think I said, and then the second condition of 30 degrees, which is scalding really if you're inside a small room. So that is my independent variable. And then my dependent variable is the instances of aggressive acts observed across these 2 conditions. It's the thing that changes or you're observing to see if it changes based on changes you've made in the independent variable. So we talked about random selection, which is when everybody in the general population has an equal chance of being represented in your experiment. In experimentation, we also worry about something else, and it's called random assignment. Okay? And this is when the sample you got from the general population has an equal chance of being included in either the experimental group that receives the manipulation or a control group that does not receive the manipulation. Okay? So what that means is, if the sample that I got in that study that I was talking about in the previous slide, which is the study on aggression, if everybody in my sample had an equal chance of being in either the 22-degree room or the 30-degree room, then that is true random assignment. They were randomly put into these conditions. And the reason for that, of course, is, and the reason why that's a strong indication of a strong design, is because we're ironing out all the individual differences that come as a package with people. Meaning that all these things that if you had selected on something else, for example, if you didn't randomly assign, for example, if you, let's say, you put everybody who showed up first in the condition with 22 degrees, and you later find out that people who are in the 22-degree room are less aggressive. Well, the problem here is, of course, is that there could be a reason why the people in the 22-degree room showed up first. And that reason wasn't accounted for in your experiment. Therefore, you don't have any confidence whether the actual change in the independent variable, the temperature, was what contributed to the change in aggressive behavior. Okay, so that's not true random assignment. So true random assignment irons out these differences and makes you more confident that the change in the independent variable, the thing that you wanted to change, contributed to a change in the dependent variable. Operational definition is exactly how I was talking about it in the previous slide again, which is when you actually be very precise about what you're going to measure and how you're going to measure it. Okay, so aggression it looks exactly like this. It looks like when somebody says a swear word to someone, for example. Aggression is also when someone raises their voice. Aggression. So this is called operationally defining what aggression is. You're putting it in very concrete behavioral terms. Of course, it's sometimes impossible to randomly assign people into conditions. And I'll give you an example when that happens. Let's say I'm comparing people who suffer from an anxiety disorder with people who've never suffered from an anxiety disorder on a particular trait. Let's say conscientiousness. Okay, so I have a group of anxious people and a group of never had an anxiety problem people. And then I find that conscientiousness is higher in the anxious condition. Part of the problem, of course, is that they weren't randomly assigned, meaning that everything that correlates with anxiety, everything that all the concepts that are associated with anxiety could have actually been contributing to the difference in conscientiousness scores, meaning that I cannot be confident that it's actually anxiety as opposed to no anxiety is the thing that is changing the dependent variable. Okay, so these are examples of quasi-experiments, and sometimes they're absolutely necessary in order for us to answer applied questions like differences between anxious and non-anxious people, different between anxious and depressed and people with schizophrenia, for example, right? People or children who are typically developing versus children who are developmentally delayed. These are, of course, you cannot randomly assign people into these conditions because these are pre-existing conditions, yet the experiments still must go on. So why do we need true experimentation, where you can actually randomly assign people into conditions? Because it is the only way, it is the best way that we have as a scientific community to actually test this thing we call causality. Okay? It is the only way, especially if it's an experiment done well, that really controls for all the confounds or all the noise. If it's an experiment done well, and there's true assignment or random assignment into conditions, then we can actually start addressing the question of causality, whether a change in the independent variable caused a change in the dependent variable. Okay, and that is an absolute necessity because it is part of the purpose of science to control and predict behavior, that we need to understand causality. We have to, at the end of the day, come up with a way to understand if A truly causes B, or if C truly causes Z, for example. Okay, and that is really a key criteria in designing interventions. For example, for psychological symptoms, in designing interventions for memory problems, we need to know what causes the change. Otherwise, we cannot replicate our findings. As mentioned in the previous lecture, there is always a trade-off in the world of science. And the trade-off is, do I make my experiment so tightly controlled so that the only thing that is left to vary, the only thing that does change is my independent variable? Or do I let go of that ideal and test it out in the real world, where my results are actually, because the real world is of course very messy, right? So you can't really create a very controlled experiment in the real world. So do I forego the neatness of a laboratory and go outside so that my results can generalize, can be applied to the general population and to general settings? So the first example of a tightly controlled experiment where all the noise is kept to a minimum, so the closer you get to that ideal, the higher your internal validity of an experiment. Okay, so internal validity is really concerned with the question, can we be confident that a change in the change that I observed in my dependent variable was actually caused or attributed to change that I made in the independent variable? Okay, so the stronger the evidence that I controlled other things in the experiment, the higher my internal validity. And then there's external validity. It's the other side of the coin. It's the trade-off, if you will. Okay, which is really, external validity is concerned with the question, can the results obtained in the study generalize to other people and other settings? So for other people outside of my experiment, it's called population validity. So if it generalizes to them, it's called population validity. And to other settings, so let's say I was doing a laboratory experiment. Now I want to try it out in the clinic, which is a real-world setting, and it replicates, then it has ecological validity. So the results are actually applicable to real-world settings as well. Okay, so that's external validity. But like I was saying earlier, there's a trade-off between internal and external validity. You can't make real-world experiments neat. You can't tightly control it, and at the same time, you can't fully generalize tightly controlled study results onto the real world, because the real world is a much messier place. So, let's stick with the idea of internal validity for a second here. Internal validity is concerned with the question, is the change observed in the dependent variable, is that attributed to change that I made in the independent variable? Okay? So that's the question that it's concerned with. And the degree of confidence with which I can answer yes to this question really depends on whether or not I controlled for other variables in the experiment that could have caused the change we observed in the dependent variable. Okay, so that noise, the noise variables around the independent variable, is what we call confounds, things that we didn't systematically control for that could have caused a random fluctuation in our data and not necessarily due to the independent variable in and of itself. Okay, so I'll give you an example of a confound. Let's say in a weight loss experiment where one group gets an exercise program and another group gets a diet. But the researchers, unfortunately, failed to tell the people who are dieting not to exercise. But they did so for the people who are exercising. They told them not to diet. And they found the results favorable in the dieting group. Of course, there's a massive confound here, which is the group that was also dieting might have also been exercising. Okay? So the degree we can control these extraneous variables, the higher our internal validity and the lower the random fluctuations and problems associated with confounds. Until next time.